Good morning, everybody. Welcome to another exciting morning of chemistry with your host, Dr. White, and that's Chem 1211. Hold on, I got something on my glasses. There. Ooh, now I can see much better. All right, game plan today. First of all, I'm going to talk about test number 4. Remember, test number 4 will be on Thursday. I'll do the same thing. Wednesday, I'll post it sometime in the afternoon in the assignment area. There'll be PDF file. I'll send out the password. I'm not sure how many versions I'll make. Actually, I am. I think I got 2 or 3. I forgot which I did. After class on Thursday, I'll send out the email. You have until sometime Friday morning, 10 or 11, I forgot which I put down, to upload it as a single PDF file. Now, there was a question from one of your colleagues at my office hour last night about the final. I do have it scheduled during final week, I believe on Tuesday at 10, but I'm going to do the same thing at that time or earlier at 10 a.m. because during finals week, we don't have classes. That's why they call it finals week. Duh. But anyways, I will send out the password. The day before, you'll be able to download the final, and I will give you till the next day. Normally, my final, if we were in a classroom, I'd give you 2 hours. Most students are done in about an hour, 15 minutes, hour, 20 minutes. I've given this finals or similar many times at COD. So that's it. So today, in a little while, I'll talk about test number 4. Then I'll go through the review for test number 4. Then I'll go through the acid-base problem set. Then I'll go through some new stuff. Don't forget Thursday the lab is due. Don't forget Thursday is the deadline for the extra credit project, which is optional, but I'd recommend you do it. And before Thursday, if you want, email me what you plan on submitting. I'll check and tell you if you need to correct something. So that way you can get 10 points. Yep, I still have 10 fingers. All right, look out, it's evolving into totally awful humor Tuesday. Actually, this is not what I want. This is what I want. All right, thumbs up, people. Everybody see test number 4 information on your screen? Come on, thumbs up, people. All right, thank you. All right, let's go through this. You were sent out this email on Friday, plus this was posted on Friday. Well, let's go through it. I'll be giving test number 4 this Thursday. I'll be emailing out the password at that time. You have until Friday, 10 a.m. to take and upload your test. The test number 4 has 9 pages, 18 problems. Some of the problem are multiple part. I think on this test, I have no multiple choice. All right, we'll cover chapters 14 and 15, dealing with rates of reaction, equilibrium, including Le Chatelain's principle, and acids and bases. Now, the point breakdown is 41 points, reaction, rate of reaction, equilibrium, including Le Chatelain's principle, and, excuse me, 64 points acid and bases. Why more on acid and bases? Well, it's more important. And it adds up to 105. So that means there's 5, yes, 5 bonus points. And as I mentioned earlier today, please note that the extra credit project is due on the 3rd. If you're planning it on, handing it in, remember, it's totally optional, but I'd highly recommend it. And like all my tests, and it'll be true for the final, I have important information for test number 4 that I highly recommend you look at. so you know what you have to memorize and what you don't. Remember, upload things properly, and I reserve the right to subtract 25 points anyone who doesn't follow the instructions. And I'd recommend on Wednesday you download the test number 4 file. There'll be a PDF periodic table and instructions, just like I've had for the other tests, how to upload it. All right. If you have any questions during the test, I'll be checking my email every couple hours. Email me. On Thursday, there'll be a normal Zoom meeting in our last lab, and I'll go over. Well, this is wrong. I won't go over the problem set for chapter 14 because we're going to do that today. All right. And I'll be posting test 4 scores by Sunday, 1 p.m., probably earlier. At that time, I'll send out an announcement and you'll get an email that the scores are in Blackboard. And by Monday, usually earlier, I'll also email, like I've done the other tests, your individual points that you get for each answer for each problem. And on the Monday afterward, a week from yesterday, next Monday, I'll go over all the answers for test number 4 in our Zoom meeting. But as always, I will delete those answers from the YouTube video, but you can always come to my office hours. And as I said here, I hope you had a happy Thanksgiving. All right, any questions on test number 4, what I just went over? Going once, twice, 3 times. All right, let's move on. For those of you who are not here and watching the videotape, you can always email me or come to my office hours. I'll have office hours tomorrow, Wednesday night, and next Monday. All right, thumbs up, people. Do you see test 4 review on your screen? Thank you. All right, let's go through things you should know for test number 4. And this review, I have both as a Word document and a PDF file in the lecture section of Blackboard for you to download if you want to. All right, first thing you should know is the collision theory of reactions. And the first thing is, what's the first important part about the collision theory? Molecules must collide for a reaction to occur. The next thing you should know is colliding molecules must have a minimum amount of energy, we call that the activation energy, for a chemical reaction to occur. And finally, colliding molecules must collide in proper orientation for the reaction to occur. So if I had 2 things I wanted to react, first of all, they got to collide. Second of all, they just can't go dink, they got to go wham. Oh, how do you like that? It's the first time I've ever used wham in a lecture, probably the last time. But anyways, they have to collide with enough energy. And finally, the orientation has to be right. Remember my key, if you put your key upside down in the door lock, it's not going to work. It's got to be oriented the right way. Now, we talked about reaction rate, and that's when you're running a chemical reaction, that's the rate at which products are made or reactants are consumed. In other words, how fast are you making something? Or how fast are you using up what you're reacting? And there's certain factors that affect the reaction rate. The physical nature of the reactants, are they solid, liquid, or gas? The concentration of the reactants, and probably one of the most important is the reaction temperature. Wow, look at all these stars. It must be important. And there's a rule of thumb that you should know. And that rule of thumb is that the reaction rate doubles for every 10 degrees C increase in the reaction temperature. So if you want a reaction, most reactions, not all, because that's why it's a rule of thumb, but about 90–95% of the time it's true, the reaction rate will double when you increase the temperature every 10 degrees C. Another way to make a reaction go quicker is add a catalyst. And a catalyst is something that's not consumed. And by the way, a catalyst works by lowering the activation energy. That's how a catalyst works, by lowering the activation energy. Now, I talked about energy diagrams and exothermic and endothermic reactions, and you should know how to draw that. Let's go through one. Everybody see A plus B goes to C plus D? Nope. Well, I better get the work done. Now can you see it? Thank you. I guess I'm going to change it. No longer thumbs up people, head shaking up and down people. All right. Question is, draw the energy diagram for the following reaction. And remember, the energy diagram on the x-axis, you have time. And on the y-axis, you have energy. Now, there's a conservation of energy. The total energy on this side equals the total energy on this side. You never create or destroy energy. And therefore, if I just say, arbitrarily say A and B have this much energy. Now, if we look at C and D and heat, have the same energy as A and B, but some of that energy is lost as heat. So for this reaction, C and D have less energy because some of it is lost as they heat than A and B. And hopefully you all remember, when you lose heat or make heat in a reaction, that's exothermic, giving off heat. And this is an exothermic reaction. And you go over the hill and down the hill to grandmother's house you go. That's an awful looking curve. But the other thing you should know, from where you start to the top, this is the activation energy. From here to here, that's the activation energy. And we went through in class how to do it for an endothermic reaction also. Next thing I talked to you about was chemical equilibrium. In a chemical equilibrium reaction, this is an example. We have both a forward and a reverse reaction happening simultaneously. Uh-oh, my tongue is working badly. But anyways, simultaneously. And you have both A plus B making C plus D, and C plus D making A plus B. And it's important that in a equilibrium, the forward and the reverse reaction rate of reaction are the same. In an equilibrium, the forward and reverse rate of reaction are the same. Now, we talked about equilibrium constants, KEQ, and you should know how to create the equilibrium constant. It's the concentration of each product to the power of the coefficient, and it's times. Common mistake here, students put a plus. No, you don't put a plus there. They see this, I think. I don't know what they're doing, except I know it's wrong. This is C to the Y power times D to the Z power. When you put it in brackets, that means moles per liter concentration per 1,000 milliliter. Then you divide it by the concentration of each reactant to the power of the coefficient. And that's how you do it. Now, how large KEQ tells you information on how far completeness of a reaction proceeds. If K equilibrium constant, KEQ, is much greater than 1, then concentration of products are much greater than concentration of reactants. If K equilibrium is less than 1, then what you know is concentration of reactants is much greater than concentration of products at equilibrium. Well, why is that so? Well, if you look up here, if this number is greater than 1, the top here, also known as numerator, is greater than the bottom here, also known as the denominator. If it's the reverse, then this is greater than this. And that's how we got that information. Now, next one is Le Chatelier's principle. And based on what a number of you have said, a lot of you are still struggling with this. So I'll let you try a problem. Dr. White's going to share today. And Le Chatelier's principle is an equilibrium shifts to the side to reduce the stress on the equilibrium. You should know the effects of concentration, adding or removing a certain chemical in the reaction, and affects the temperature if you have an exothermic or endothermic reaction. And remember, boiling water adds heat. Ice bath removes heat. Nod your head, people. Can you see A plus B equilibrium C plus D plus C? Thank you, nod your head, people. Hang in there. I'm writing. If you were in a classroom right now, you'd be watching me right on the whiteboard. All right, let's take a look at this reaction. It's an equilibrium reaction. What happens to the concentration of A and C if A, you add more B, B, you remove B, C, you put the reaction in a beaker of boiling water, and D, you put the reaction in an ice bath. And it's your time to have fun. So enjoy, courtesy of Dr. White. By the way, it's permitted to give me nasty, dirty looks now. One of these years, I'm going to get that game show music playing in the background. Dun, 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 dun. Never mind. Just lost everybody. I don't know what happened, but I hope the computer gods are not mean to me today. Please. All right, you should see the problem. Everybody see the problem on the screen now? When you're done, give me a thumbs up. Give you about a minute or so more because a couple people are done already. All right, anybody need more time? Yell out. All right, let's do it. This is Chatter's principle. I'm asking what happens to the concentration of A and C if you add more B. Well, at equilibrium, there's a certain amount of B. Now there's too much B. And the equilibrium reaction says, oh no, I have too much B. How do I get rid of it? Well, if A reacts with B, B is consumed, you'll have less. Well, when A and B react, it goes this way to make more C and D. So A and B react, B is consumed, so is A. Therefore, A, you'll have less, it will decrease. You'll make more C, so that will increase. If I can spell it right. Now, what happens if you remove B? Well, at equilibrium, there was a certain amount of B. Now you've taken some away. So the equilibrium says, oh no, we don't have enough B. We need more B. Well, how can you increase the concentration of B? Only one way. C and D react to make more B and more A. Well, C reacts with D, C is consumed. When something is reacting, it consumes, therefore the amount will be less and it will decrease. And since you're making more B, you're going to make more A. The concentration of A, since you're making more of it, will increase. Now, if we look at what happens when you put it in boiling water, remember, boiling water adds heat. Ice bath removes heat. That's why you feel cold when the temperature is colder if you stick your hand in an ice bath, because you're losing heat from your body. That's why you shiver. So if we put it in the boiling water, what have we done? We add heat. At equilibrium, there's a certain amount of heat. And now you've added heat. And there's more heat than it should have. Uh-oh, D just disappeared. Hang in there. It's back. So at equilibrium, there's a certain amount of heat. Now there's too much heat. So how can it get rid of the excess heat? C and D react with heat because the heat will now be consumed to make more A and B. Well, if you're reacting C and D together, that means concentration of C will decrease. And since you're getting rid of the excess heat by reacting C, D, and heat, you're making more A and B. Well, if you make more of something, A, you're going to have more of it. And finally, let's look at D. And D, what are we doing? Putting it in an ice bath. Oh, look, over here, someone was nice enough to put on the screen, an ice bath removes heat. Oh, that was nice, whoever did that. And now, at equilibrium, there was a certain amount of heat. And now we've removed it. And the equilibrium says, oh no, we don't have enough heat. We need more heat. Well, how can you make more heat? A and B react to make more C, more D, and more heat. Well, if A and B are reacting, A is being consumed, there'll be less. So the concentration of A will decrease. Now, if A and B are reacting to make more heat, they also make more C and D. Well, if you make more of something, you'll have more of it. Oh, that's profound. And therefore, the concentration of C will increase. And that's how it works for an exothermic reaction. If the heat were on this side, you'd use the same type of logic. Are you adding or removing heat when you put it in an ice bath? And how do you replace or get rid of excess or not enough? All right, next, let me check. Everybody see acids and bases on your screen? Thank you, thumbs up and head, shake your head up and down, people. All right, you should know what is an acid under the Bronsted-Lowry theory of acids and bases. And an acid is a proton donor, proton being H plus. You should know that. A base is a proton acceptor. Now, their key acids you should know. The formula, if I ask on a test, is HCl an acid or base? You should know this is an acid, hydrochloric acid. Is H2SO4 an acid or base? It's an acid. Sulfuric acid, and finally HNO3, nitric acid. These are all acids, and you should know that. On bases, we have sodium bicarbonate, sodium hydroxide, potassium hydroxide, and ammonia. Now, one I didn't have, but you really should know, is sodium bicarbonate, which is also known as baking powder. Now, when we have water, water can react with itself in an equilibrium. If you have two water molecules, they'll form the hydronium ion and the hydroxide. Now, hopefully you can all see how little the top arrow is here? Because the equilibrium is mostly to the left. Well, chemists came up with KW. No, it's not named after me, but I like to think so. Makes me happy. And KW, ionization constant for water, is the hydronium ion concentration times the hydroxide equal to 1 or 1.0 times 10 to the minus 14. And this is for room temperature, which for our class is what we'll use. I will give this to you, important information. Now, you should know, when we talk about an acidic solution, that means the hydronium ion concentration is greater than hydroxide concentration. And this is acidic. Now, basic solution, the hydroxide concentration is greater than the hydronium ion concentration. And finally, a neutral, by the way, that's sometimes called alkaline, like your alkaline batteries. And neutral, the hydronium is equal to the hydroxide ion concentration. Now, this is pretty awkward to look at numbers, which is greater and all that. And somebody came up with the pH concept. And the pH concept is a small number, scale of small numbers used to specify the molar hydronium ion concentration. And the important thing is this is an aqueous solutions, meaning water. By definition, the pH is equal minus the log of the hydronium ion concentration. And my special gift to you is if the hydronium ion concentration is equal to 1.0 times 10 to the minus x, then the pH is x. Again, pH equal minus the log of the hydronium ion concentration equal minus the log. And if this is 1.0 times 10 to the minus x, then this is equal to x. Now the pH scale, ooh, look, I have down here important. Nah, that's not good enough. pH goes from 0 to 14. In the middle is 7. When you're at 7, hydroxide equals hydronium, it's neutral pH. When you're below 7, it's acidic. When you're above 7, it's a basic. The closer to 0, the more acidic. Closer to 14, the more basic. And time to gross you out time. And that is in your stomach, the liquid in there, what do they call them? The stomach juices, or doesn't sound appealing, but whatever liquid's in there, stomach fluids, that sounds more. Anyways, it's acidic. Why? Well, remember, this is chemistry, not biochemistry or organic chemistry. Why? Because there's an acid present. The pH is less than 7. It's acidic. Now, in real life, it helps break down food, but I'm not teaching you that here. Why is the pH of your stomach below 7? Because there's an acid present. Now, I always think of one of the great miracles of life is I, and also you too, have cells in your stomach that make hydrochloric acid. That just amazes me. Oh, wow, I can do that. And it is that oh, wow type thing. Oh, by the way, acids, especially weak acids, are very sour. And if you ever bite into a lemon or a lime, why is it sour? Because it's got an acid present. In those cases, citric acid. Now, the pH is from 0 to 14, never lower than 0, more than 14. The lower the pH, as I just mentioned, the more acidic a solution is. The higher the pH, the more basic it is. It's a logarithmic scale, which means each number is a power of 10. I won't ask that on the test. Now, everybody see buffers on the screen? Thank you. Now, buffers are a solution that resists major changes in pH when a small amount of acid or base are added to it. Again, buffers resist major changes in pH. In other words, pH stays the same when you add a small amount of acid or base. Now, a very important thing, 10 points, we'll go through that today in the problem set, and that is titrations. And that's where you add a base to an acid, neutralize it, and get a salt, and you bring the pH to 7. And we have what's called pH indicators that change color at different pHs. The most famous is phenolphthalein, which changes color at 7.0. One molecule more and it changes color. And in a titration, which we'll do a lab this Thursday, you will, moles of acid at neutralization equals moles of base. And for a monoprotic acid, which I always do for this class, milliliters of acid times molarity equal milliliters of base times molarity of base. And 3 of these you'll be given, both milliliters, and 1 of the molarity, either acid or base, and you'll be asked to calculate the other one. And that's how you do it. And we'll go through that in the problem set. All right, any questions, first of all, about the review and test number 4? Hold on, test number 4 likes to go there. All right. That's not what I want. All right, where'd you go? All right, give me 1 second to clean up something. All right, sorry about the delay there. Does everybody see practice problem chapter 14? Yes, thank you. All right, let's go through this. If you have any questions, always feel free to ask me, because remember, there's no such thing as dumb question in my life or in my class or anywhere around me. All right, you should know, what is an acid per Bronsted-Lowry theory of acids and bases? And it's a proton donor. What is a base? A proton acceptor. Now, let's look at the following. You should know which of these are acids and bases, and or a salt. And if we have HCl, that's the hydrochloric acid, NaOH, sodium hydroxide, a base. You see OH in the molecule. For this class, it's going to be a base. And NaCl, oh, please pass the NaCl, that's salt. And H2SO4, sulfuric acid. NH3, ammonia, is a base. And HNO3 is an acid. Now, let's look at, number 4. If a solution has a hydronium ion concentration H3O plus equal 1.0 times 10 minus 3, what is the pH of the solution? And is it acidic, basic, or neutral? We're trying to find the pH first. We're given this. You're given, this will be in test number 4, important information, pH equals minus log, hydronium is 1.0 times 10 to the minus 3. Remember, when the hydronium is 1.0 times 10 to the minus x, the pH is x. In this case, x is 3, and therefore it's 3. Now, oh, look, someone wrote something useful on this over here, and you should know this will not be given to you. It's probably one of the most important things I'll teach you this whole semester. pH scale, 0 to 14. 7 in the middle is neutral. Below 7 is acidic. Above 7 is basic. Hopefully you all know that 3 is less than 7, so this is acidic. If we do the next one, we get a pH of 7, which, if we look at here, is neutral. If we do number 6, again, here's the hydronium ion concentration. You're trying to do the pH, and also is it acidic, basic, or neutral? pH is minus the log of the hydronium. Put that in. X is 12. 12. And if we go back up here, hopefully nobody's getting dizzy. pH scale above 7 is basic. Hopefully all agree 12 is above 7, so the solution is basic. Now, let's look at the next one. If a hydroxide ion concentration is 1.0 times 10 to the minus 3, what is the pH of the solution? Is it acidic, basic, or neutral? Now we're trying to find pH. We're given hydroxide, but oh no, pH is minus log of the hydronium, not hydroxide. So now I need two steps. In step one, I solve for hydronium. How do you do that? You'll be given hydronium times hydroxide equals 1.0 times 10 to the minus 14. I want to solve for hydronium. I got to get rid of hydroxide, so I'll divide by it. Remember, anything divided by itself is the number one. But whatever you do to one side, you have to do to the other. I did. Anything divided by itself is 1, so hydronium equals 1.0 times 10 to the minus 14th divided by hydroxide. I put it in there, and I get 1.0 times 10 to the minus 11th is the hydronium ion concentration. Am I done? No, I'm trying to find pH. How do I do that? You need step number, anybody see my 2 that goes there? It ran away. Oh no. Anyways, pretend there's a 2 after the ampersand sign. Step 2, solve for pH. pH equals minus log of hydronium. We just calculated that, so I'll put it in. And when x is 11, and this is 1.0 times 10 to the minus x, the pH is x, and that's 11. And remember, below 7 acidic, 7 neutral, above 7 basic, and hope we all agree that 11 is greater than 7. That was one of the requirements I never mentioned. You got to know the numbers 0 to 14, which ones are lower and larger and smaller than each other. How do I mean this semester? All right, any questions on that one? Remember, everything you see here is available on problem set answers in Blackboard. If I look at the clock, we're just about ready for a break. So what I'm going to do right now is take a break. I'm going to do some stretching, which is good. Dr. White's back is almost back to about 95%, which is very good. I shouldn't bring religion into the classroom. And also thank you to the people at NCH Physical Therapy Group here in Schaumburg. All right, see you in 5 at 10:55. That's when the big hand is on 11. For those with digital watches, that's when it's 10:55. Bye. I'll be back in 5. Oh, I get to call you all back to start. It's time to start again. All right, let's get going. We just did this problem. Let me just check. Everybody see problem 7 on the screen? Good. And I'm not going to do another one or a third one. You can go back and look at these. Now, here's some more important thing. What happens, notice it says there to the numerical value of the pH of a beaker at pH 7 if you add a few drops of concentrated NaOH solution. Well, you have to know that's a base. And when you add a base, it becomes more basic, the solution, and the pH increases. When I add a base, the pH increases. When I add an acid, the pH will decrease, the numerical value. Now, what happens to the pH if you add a few drops of concentrated H2SO4? Well, I'm testing, do you know H2SO4 is an acid? And the answer is, I do. I'm a chemist, I know these things, and you should know them now. And when you may add an acid, the pH will always decrease. Now, let's look at number 11. What happens to the numerical value of the pH of a beaker of buffer solution? And here the important thing is buffer solution. If you add a few drops of a dilute acid, buffer solution by definition resists change in pH if you add a small amount of acid or base. Therefore, you add a small amount of acid, dilute acid, a small amount, it stays the same, the pH. What happens if you add a few drops of a dilute base? It stays the same. All right. Now let's look at number 12, 10 points. If you have to add 1.35 times 10 to the third milliliters of a 1.53 molar NaOH solution to neutralize 1.87 times 10 squared milliliters of HCl solution, what's the molarity, excuse me, I'm getting choked up over this stuff. Strong acid and base stuff might do that to me. Oh, that was lame. But anyways, what are you being asked to find? Molarity of HCl, which is an acid. What are you given? The milliliters and the molarity of your base. You're given the milliliters of your acid. At neutralization, moles of acid equal moles of base. Moles of acid, this you'll be given, is milliliters of acid times molarity of acid equal milliliters of base times molarity of base. What are we being asked to solve for? Molarity of acid. This line should have been over here, sorry. And milliliters divided by milliliters equals molarity of acid. On whatever you divide this side, you have to do this side. Therefore, this becomes milliliters of base times molarity of base divided by milliliters of acid. Put the numbers in. On test number 4, like all my tests, please use proper significant figures for all calculated answers. When you do a multiplication division, you get the same number of significant figures in your answer as the number you multiply and divide as the fewest. Uh-oh, he's in his 3 significant figure, right? 3, 3, 3, and the answer is 3. Significant figures, and it's 11.0 molar HCl. On this one, I did it correctly. Let's look at number 13. You have to add 150 milliliters of a 0.333 molar HCl solution to neutralize 211 milliliters of an aqueous NaOH solution. What is the molarity of the NaOH solution? Well, what are you trying to find? The molarity of NaOH, a base. You're doing a titration. When you see at neutralization, that should be the key word. This is a titration. And when you have a titration, moles of acid equal moles of base, which is equal milliliters of base times molarity of base times milliliters of acid times molarity. You want to solve for molarity of base, NaOH. Divide this side by milliliters of base, this cancels out. Molarity equals milliliters of acid. Molarity of acid times milliliters of base. Put the numbers in, and you get 0.181 molar NaOH. And the next one, same thing. I'll let you go back and look at it. And that's problem set acids and bases. And let's do something I think will be beneficial. All right. Everybody see test 4, important information? Thank you. You should go back and review this. This is in the lecture folder of Blackboard. The last 2 pages of test number 4 will be this. Here I give you a Chandler's principle. I give you pH, and I tell you if hydronium is equal 1.0 times 10 to the minus x. This is what x is. I give you the ionization constant for water, and I give you titration. You got to memorize how to do the equilibrium constant, but I've cut down on memorization. In the past, all that you see on these 2 pages, you would have to memorize too. All right. I'm going to do something that I think you might enjoy. So click. I'm turning the switch. Will this be on test or final? Off. Now, the house I live in now, I've been here over 20 years. When I bought it new, about 2 weeks after I was living here, my kitchen sink stopped up. And I figured, well, the previous owner or his wife probably dumped grease down there. Grease from cooking things with fat and oil will clog up a drain. So I figured, all right, new house, let me get off to a good start. And I called the Roto-Rooter guy and came out and, Roto-Rooter. And, oh, you're open now. A week and a half, 2 weeks later, clogged up again. And I have a warranty, by the way. Being a senior manager in industry, I know how to press on people. I call it being aggressively assertive. I'm good at that, sometimes too good. Anyways, I called him up politely and said, it's clogged up. Oh, it's under warranty, I'll be out. So he does the same thing. Oh, it's open again, you're good to go. Thank you. And about 2 weeks later, it clogs up again. Now, Dr. White is not happy. Why? Because I'm working full-time in industry. And it's not the money. It's the fact I'm wasting time waiting for him to show up because I live alone to do what he should have done right the first time. Well, he comes and apologizes and says, also besides rhodoruria, I'll put this chemical down there. It'll clean your drains. I looked at the bottle, being a surfactant chemist who knows surfactants. I looked at the label. I thought, oh, this is garbage. It ain't going to do nothing. And guess what? A week or so later, it clogged up again. I said, I've had it. I'm not going to bother with this guy. Hell with the heck with the money. Oops, yeah, not going. But anyways, so I went to my local Home Depot, and I'm in the Schaumburg area, and the one on Barrington Road. Those people are magnificent. They're so helpful and knowledgeable, and they've been doing that for many years now for me. And so I go, and you see this long wall of drain cleaners. I pick one up, Drano is a known. I look at the back because I've never needed one for that. I lived in apartment buildings. You had a janitor do that for you if you had a problem. So I looked at the back and I saw, oh, hydrochloric acid. It didn't say hydrochloric, it said, maybe it did. I said, oh, that's an acid. I pick up another one, acid. They're like a whole wall of different brands. And one of the nice people working that area came up to me and said, can I help you, sir? And I said, sure. And sometimes Dr. White uses his brain and thinks. And I asked the gentleman, all these drain cleaners, which one do the plumbers buy? Without even thinking, he says, that one. Hold on while I go out to the internet. Everybody see the black bottle on your screen? There are a couple of them. Thank you. And this is the one he picked up. And it's got the real fancy name, hair and grease cleaner, drain cleaner. And it was the only one in the whole wall, and to this day it's still that way, that's in a thick Ziploc baggie that says on the baggie, use proper eye protection when using this product. And he says, this is the one. So I pick up the bottle, look at the back, and what do I see there? I see sodium and potassium hydroxide. I said, oh, that's a base. He said, no, it's an acid. I said, look, excuse me, but I have a PhD in synthetic organic chemistry. I'm an industrial chemist who've been working in chemistry for decades now. Come on, I know of acid from a base. It's a base. He said, no, it's an acid. I figured, all right, the guy helped me. I learned a lesson in Home Depot. Don't argue chemistry with the people there, even if you have a PhD in synthetic organic chemistry and know your stuff. I thanked them, took it home, followed their directions. By the way, yes, I put on safety goggles. I wore gloves and I have lab coat. If I didn't, I'd wear a long sleeve because you don't want that on your skin ever because it will damage your skin. And I know how to handle it. And I was careful. I followed directions. And lo and behold, it was clean. I figured I'll do it a second time just to be safe. And for 15 years later, it didn't clog up, but I've always kept a bottle of that in my house. And when it did clog up, did the same thing. About 3 months ago, my drain in my bathroom, back over there, notice I'm pointing to like you know where it is. But anyways, it was clogging up. And I figured, all right, and it was going slower and slower. I said, all right, stop procrastinating, get the hair and grease remover. I put it down. I figured I've been here almost 20 years. And I've never had to clean. I'll let it sit overnight in there. And they say if it's real bad, let it sit longer. And I come back next morning, pour water down there, have the eye protection on, all that. And lo and behold, it's like it's brand new, like it was never clogged. And I've had many students who've had either kitchen or bathtub drains and use this product, and they all come back with the same thing. It works. So if you ever get a clogged bathroom sink, bathtub, or kitchen sink, go to Home Depot. I've never seen it sold at Menards or Lowe's. By the way, I don't get any kickback from Home Depot. I wish I could, but I don't. But this is stuff to buy. And if you look in my utility room, I have almost a full bottle of this. And because it's inorganic, it will last for almost ever, I don't know about ever, but for many years. So if you keep a bottle around, and this is the size I keep, and when it runs low, I'll go out and buy another one, and it works. Oh, by the way, another thing which we really don't cover in there, but a plumber told me when I had him out for doing something else with the tree, and I asked him, you see all those, and I didn't realize in the older homes, in your house, in the drainage at the very bottom, going to the sewer, a lot of times you have metal pipes, and it's cast iron. Acid will react with cast iron and eat it away. Base won't. So that's another reason to use hair and grease, as opposed to the other ones, which are all acids. And that's a nice public service announcement from me, your host, Dr. White. Stuff really works well. All right. I'm going to be covering stuff that will not be on test number 4, but will be some of it on the final. And thanks everybody for enjoying my story, but I pass along. I think Thursday we'll have time. I'll teach you, usually I do this in organic chemistry, but I figured I'll do it for you too. I'll teach you how to clean a bathtub with a lot of bathtub scum in about 30 minutes, where 20 minutes or more of that, you're just waiting for something to happen. And the actual scrubbing, about 5 or 7 minutes, and not even hard scrubbing. That's the one thing in the world I hate the worst is cleaning the bathtub, because if you use bathtub bar soap, you get the scum, and I'll teach you, because a couple of years ago I said, why am I spending all this time scrubbing? I'm an organic chemist. I know chemistry. Use your brain. And I did, and it works. It still does. All right, I'm going to go through chapter 16 in 5 minutes or less, because I'd rather spend time on stuff that's more important in your life than stuff you probably never use. I didn't say that. Remember, I didn't say that. But it's important. If it was a 2 semester and we had more time, I'd like to cover this, but we don't. And I've zeroed in on things that are more important. All right, everybody see chapter 16, oxidation reduction. Switches off totally, totally, totally. I just want to cover this real quick because it's in the active course file, and I can honestly say I covered it. Dr. White doesn't lie. Now, there's certain types of reactions called oxidation reduction, where you react two things together, and it's an important part of our life. An example, rust that forms on your car is an oxidation reaction. Now, the term oxidation came originally because oxygen will cause certain things. Rust is formed from the oxidation caused by the reaction of oxygen with the iron in your car, especially if you don't have the paint on there. You got the coating, which is the paint, is taken away from the metal, it will rust. Now, when you have an oxidation, again, the switch is totally off, you have a loss of electrons. And a reduction, you gain electrons. So you have both oxidation and reduction happening at the same time. Because one chemical will lose or element will lose electrons, the other will gain. How can you tell that? Well, first of all, there's a term reducing agent is something that is oxidized. It's the opposite of what you think. An oxidizing agent is something that is reduced. The oxidizing agent oxidize the other things. Now, important thing of this where you have oxidation. How many of you ever picked up a cracker and, ooh, that tastes awful? Or you smell butter and it went rancid? That's because the oxygen in the air reacts with certain molecules and breaks them apart. It's called oxidation. Now, there's certain things, chemicals you can add that slow that down or stop that. And those are called antioxidants. How many of you have heard of antioxidants? And those are chemicals that stop oxidation. Now, about 2 or 3 years ago, I heard, and I read a couple places, and I have no idea if this is true, that first of all, I think you all know that antioxidants are healthy for you. That part I do know is true. Like Popeye getting your spinach. Spinach has a lot of antioxidants, and other things have antioxidants. And uh, the theory was that aging in our body is caused by oxidation reactions. And if you eat antioxidants, that slows it down. Is that true? Don't know. And I'll be honest about it. But some of the things they say, every once in a while you hear drink a lot of red wine because that has got rich antioxidants, or eat dark chocolate. I wonder if a person who did that just wanted to convince his mother you should eat dark chocolate. But anyways, I have no idea how effective those are, but antioxidants have been good for you and are good for you. And elements have what's called oxidation number, says how many electrons can be lost or gained. And that helps you determine if you have oxidation reduction. If you have an oxidation, the oxidation number increases because you lose electrons. If you have a reduction, something is reduced, you have gain of electrons, and that decreases the oxidation. I'm not going to teach you that. Students have really a lot of trouble with this. Now, one of the most important things where oxidation reaction occurs are in batteries. I think we all use batteries, also known as electrochemical cells, and also known as voltaic cells. In other words, there's a battery in your car or your father's car, mother's car, neighbor's car, and that's got chemicals in there that react to form electricity. And that's an oxidation reaction. If you have a cell phone, you have a lithium battery, whatever, and that's undergoing oxidation reduction reaction to make electricity. Now, again, switches off. An anode is where the oxidation occurs, and it's the negative part of the battery. And the cathode is where the reduction occurs, and that's the positive end of the battery. Switches off, and batteries are used to power everything, and they're redox. Redox is shorthand for reduction oxidation reaction. And there are different types of batteries. Electroplating is another example of redox. And that's everything you want to know in a couple minutes or less about oxidation reaction. It will not be on test number 4. It will not be on the final. All right, everybody see chapter 17. All right, for part of this, I'm going to turn the switch full blast for the final, not test number 4. All right, let's talk about nuclear radiation. Now, I could probably give a whole semester course or someone else who knows more about it, because Dr. White is not a nuclear chemist. I never wanted to be one. It's quite hazardous at times. In fact, a number of years ago, and this is a sad story, I was at a party and a number of the scientists there were from Argonne and Fermi Labs. And there was this one nice lady, but she looked sort of sad, and she was there, but you could tell she didn't want to be. And I asked some other people, what's going on with that woman? Well, she just lost her husband. I said, well, I'm sorry to hear that. What happened? Well, he died of this very, very rare lung cancer. He worked at Fermi Lab with radioactive material, and I didn't have to be told anything. Somehow he had gotten exposed to radiation and gave him cancer and killed him. And that's why Dr. White stays away from stuff like that. Even though organic chemistry, a couple of times I came that close to not being here. Okay, I was able to solve a problem, and I'm alive. Thank you. But radiation, radioactive chemistry is important in our daily life. All right, switches off for this slide. What's a radioactive element? That's an unstable isotope of an element that will emit energy spontaneously to form a more stable isotope. Again, switches off on the slide. What's isotope? That's a compound that has the same number of electrons, same number of protons, but different number of neutrons. And certain isotopes are radioactive of certain elements. And when they change, they give off radiation. And like I have here, the energy emitted from a radioactive isotope. If you have uranium, it gives off radiation. Radon in your basement is dangerous because that gives off radiation. I don't have a problem, but my best friend in Indiana had a problem with that, to the point where in a number of houses in the Midwest, in his basement, he has a very dark, deep basement. He has a air pump that continually pulls air out or refreshes the air in his basement, keep the level safe. Even though I kid him, oh, are you losing more hair? Actually, he lost most of his hair by the time he was 30. I was lucky, I still have some of mine. But anyways, that's a joke. Don't tell him I said that. All right, now, next couple of slides, still off. Now, what are different types of radiation? One type is called the alpha particle. And the alpha particle, that comes from the Greek letter alpha, again, switches off. That's alpha. Yes, Dr. White knows most of his Greek alphabet. And it's a particle that contains 2 protons and 2 neutrons. It's emitted by radioactive nuclei, which is another way of saying isotopes, and it has a positive charge. Neutrons 0 charge, protons plus charge. Now, the beta particle, oh, my Greek alphabet is good today, is a particle whose charge and mass are identical to electron, are emitted by radioactive nuclei. As you know, electron has a negative charge, switches off. Now, why they just didn't call it an electron, don't know. I guess it's radioactive, so you got to say it's a different name. You can tell Dr. White is not a nuclear scientist, or won't be. All right, and another one is called a positron, and it has a positive charge to it. Switch is still off. And finally, we have very high energy called gamma rays. And gamma rays are a form of high energy radiation without mass or charge. This pure energy are emitted by radioactive nuclei. Now, one thing I do have to warn you, in our universe, unless I got stolen to another universe, gamma rays will not turn you into the Hulk like Bruce Banner. I see a lot of you don't know your Marvel comics. Dr. White has been for many years in Marvel comics, the Hulk, Thor, Spider-Man. Thor was my favorite always when I was a kid. And unfortunately, when I got to college, my mother said, "Oh, you don't need these comic books," and she threw them away. And if I had them today, they'd be worth thousands of dollars. But can't change the past, because I had a Thor 3 and 4 and 5 and 6. I never got kept, or I saw, but I never got, because I got into it a little late, 1, 2, and 3. And even those 4, 5, and 6 and later are worth a lot of money today. All right. Now, when we say something decays, radioactive decay, switches to off, it's a process in which a radioactive nuclei, otherwise known as an element, is transformed into a nuclide of another element by the emission, or the result of the emission of radiation. It gives off some form of radiation and changes from one radioactive element to another, or maybe non-radioactive. And the emission that's given off is called the alpha, beta, or gamma rays. Switches on. Warning, switches on. I've just turned it up to 20, even though it only goes up to 10. And let's talk about half-life. Oh, it even says no. Oh, let's improve on that. Now, what's the half-life of a radioisotope? That's the rate of decay, and what it is the half-life, which is abbreviated by T1 half. T1 half is the amount of time required for 1/2 of any quantity of a radioactive element to undergo decay to something that's not radioactive. So this is the amount of time. Now let's go out into the real world. Hang in there. Now, let me check. Everybody see radiometric time scale on your screen? You see it? Thank you. Now, one of the things that people never realized, or they didn't really advertise about radioactive materials, or more importantly, radioactive waste, is its half-life. How long does it take before half of the weight, if you had 100 pounds, before half of it's no longer radioactive? If you look at uranium-235, which is a radioactive element, like a waste from radioactive nuclear reactors, it takes 704 million years before, if you had a ton of it, after 704, let's just call it 700 million years, you'd have half of it. In other words, it's going to stay radioactive for a long, long, long time. Now, a while back, and let's see if I can find it. Now, back in the late 1980s, our government, someone came up with this great idea. Well, we got all this nuclear waste, and it's a problem. What do we do with it? They say nuclear energy is clean. No, because you're left over with the waste. And to this day, most of it's being stored on sites where the nuclear reactors were. Uh, Not to scare you, but I will. I don't know if they cleaned it up or not, but uh, ComEd and their whoever their Cal, whatever the company that owns them now has up by Northwestern Evanston used to have a nuclear reactor only a couple miles from Lake Michigan, and they stored tons of nuclear waste there. If it leaked, guess what? There goes our drinking water. You're dead, or not dead, no water. I don't know, hopefully they've cleaned it up, but I don't know. Well, the government came up with this great idea, not, and they said, let's go where there are not a lot of people. So they found this mountain range with salt mountains they could dig in and have these big vaults that would be stable. It was about 50, 100 miles from Las Vegas, and we'll ship all our nuclear waste and store it there. Two problems. How many people want nuclear waste being shipped through their state? How many people in Nevada want to be the waste center for all nuclear waste in the United States? Well, anyways, they went ahead and built a lot of it and wasted a lot of money. And the scientists said, oh, we've come up with these very special waste containers that will store the waste. And they tested it. And these are containers that have to last millions of years. Within about 5 years, they're leaking. Right. Well, the place they did it is called Yucca Flats or the Yucca Mountain Nuclear Waste. And I don't see here where they talk about the storage containers, but trust Dr. White, they messed up. Now, again, what's the half-life? The half-life is the amount of time it would take for half of the material to no longer be radioactive, undergo decay. Everybody see the pH scale on the screen? All right, come on. All right, let me decode this, decay it. That was good. But anyways, Dr. White just came up with a new compound. Just for you people only. All right, chemium original, have a half-life of 4 years. If you have 800 grams of chemium, then how much chemium will you have after 8 years? Now, I could show you this very fancy formula, but if I give you a certain type of problem, which I will on the final, if I put it on there, this is how you do it. All right, the half-life tells you every 4 years you'll have half of the chemium. So we have 800 grams, start with. After 4 years, you'll have half of that, which is 400 grams. And after 4 more years, total of 8, you'll have half of this, which will be, if I did my math right, 200. And that's how you do it. Again, half-life tells you how much you'll have after a certain period of time. And next, probably Thursday, I'll do another one of these. I don't have a problem set because it's pretty straightforward. All right, switch is still at 20. I don't know why my pen didn't go red. Hold on, I'm not going to cheat you out. Now, when we talk about nuclear chemistry or nuclear energy, there's two main types of nuclear reactions. One is nuclear fission, the other is nuclear fusion. Now, nuclear fission, is when you bring two large nuclei, high atomic number radioactive materials together, or large, I take it back, when you have a large nucleus, high atomic number, and splits into two medium. And this is like taking uranium, and when it splits, it gives off a large amount of energy. Now, that energy can be used to heat water, to make steam, to drive a turbine, to make electricity. And that's how nuclear reactors work. And you should know that nuclear fission is used in nuclear reactors. So when you have a large element and it decays to something smaller, that gives off a lot of heat, and that's fission, nuclear fission. The other one is fusion. And nuclear fusion is different. This is when small nuclei or elements come together to make larger ones. And when that happens, also a lot of heat is given off. And you should know, where do you find nuclear fusion? Guess what? The sun. The sun, you have hydrogen coming together to make helium. And under the stresses and gravity of the sun, that happens, it gives off a tremendous amount of heat. Now, here's something that's always been helpful. Fusion, U, I think of sun, U. Therefore, whenever I see fusion, I think of the sun. And the other one, fission, no U, I think a nuclear reactor. And therefore, you should know on a test, if I ask you, give an example in our daily life that uses nuclear fission, it would be a nuclear reactor. If I ask, give an example of nuclear fusion, the U gives it away, the sun. Not that I want you to hurt your eyes, but the next time you see sunlight, or if you have special glasses to look at the sun, think about that. That's nuclear fusion, hydrogen atoms coming together to form helium. at such a high energy that it gives off all the heat that keeps us alive, which is pretty good. And with that, I'm done for today. Don't forget, let's see, today's Tuesday, Wednesday night. If you have any questions, come on by my office hours, 6 to 7:15 on our favorite Zoom channel for office hours. And if you have any questions, always feel free to email me. Also, let me remind you, if you're doing the extra credit project you want, send to me before it's due and I'll check it. Send it by email. And don't forget to uh, make sure it's uploaded by the due date. With that, I can use this. Love it. With that,
Dr. White, I have a question.
let me finish up and I'll answer your question. With that, I'll say, gang gazoon, goodbye. Be healthy, be safe out there. It's getting more dangerous out there. And with that, I'm done.